Appreciate that. My name is Mohan Puntambekar. I am a field applications engineer at Anritsu. And the topic of discussion today is IMD measurements on the VectorStar, where we would be specifically talking about the IMDView software, which enables us to do intermodulation measurements on the VectorStar network analyzer. So initially, I'll give a bit of a background on linearity, IMD, why we do that, and so forth. And then we will speak about the configuration panel itself, the IMDView software. And then we will go through the various settings in that panel. And then we will speak about the dual source and the combiner, which is what I would be using on my VectorStar. Then we will briefly cover the power and receiver cal that needs to be done for the two tones that you inject into the device under test. And for this case, the device under test is an amplifier on which we will be performing the IMD measurements. And then we will conclude with a summary of the benefits for the IMDView software. So let's begin addressing linearity. Now, what is linearity? Basically, all linearity is the behavior of a circuit where the output signal strength varies in direct proportion to the input signal strength. What does that mean? Very simple example. If you have an amplifier with a gain of 10 dB and you begin with putting in minus 10 dBm at the input, and at the output in its linear region, you're going to see 0 dBm. Now you keep increasing the power right up till, let's say, 0 dBm at the input. Now you expect plus 10 dBm at the output in accordance with a gain of 10 dB. But if you don't see that and the gain drops, for example, to 9 dB, then the device has become nonlinear and it's entered compression. So that's not the linear region of the amplifier. IMD is basically one way to measure linearity of a device. Some effects of nonlinearities include harmonics, interferences, and saturation. And then some measurements which characterize linearity are the intercept points, the spurious free dynamic range, which is actually a ratio of the fundamental signal to the strongest spurious signal at the output. And then you have the compression point also. So these are the few ways you characterize linearity. IMD is one of them. And for this purpose of the webinar, we will be focusing on the IMD measurements. So how is IMD carried out? Basically, it involves injecting two or more signals into the input of a nonlinear device. In this case, it's an amplifier. Now, you can inject more than two tones also, but then as you can imagine, the math becomes very complicated. So generally, it's an acceptable practice to just inject and carry out the analysis with two tones. Now, as you can see here, when you inject two tones into a nonlinear device, you can get all sorts of products. The ones that are of interest are the third order ones, as you can see on the plot from the bottom right. Especially the particular combination of interest is the 2F1 minus F2 and the 2F2 minus F1 products, because they fall in band. And most folks in the industry actually focus on an analysis of those products, the third order products. They are called the IM3 products. Moving on. Just wanted to quickly address intercept points, what they mean. So this is just a graph. The blue trace there is the original tone. What this graph shows is power in versus power out, and the slope of the blue tone in the linear region is 1:1, meaning if I increase the power by 1 dB, the output should also vary by dB for dB. Obviously, you have the gain. You have to take the gain into account also. At the same time, if you look at the slope of your third order products, they vary 3:1 ratio, meaning if I increase the power level at the input by 1 dB, the power of the third order products increase by 3 dB. And then on the right, there's a little table there, what I mean by order of the products. So in other words, if you have a fifth order product, for example, you have a 3F1 minus 2F2, where you just, 3 plus 2 is 5. So that's a fifth order product. In the fourth order product, you have 2 plus 2, and that's 4. And so forth. Now, as far as amplifiers are concerned, they talk in terms of output IP3. That's the output referred IP3. And again, as explained in the previous plot, you can see on this plot here that as the product, as the power of the fundamental, that has a slope of 1:1, and the slope of the third order product has a slope of 3:1. Now, in theory, there comes a point where you are increasing the power and the level, and then there's a theoretical point, the output IP3, where the power levels of the fundamental and the third order product are the same. Obviously, it'll be very difficult to measure it because you would need to put in super high power into your device under test, but it can be calculated. And there's a little formula there. Output IP3 is given by the IMD3. Now, as you can see from plots later on, which I have in the slides, IMD3 is the difference between the fundamental and the third order product, the power level difference. And it's that divided by 2 plus the output power gives you the output IP3. For devices like mixers, for example, you can think in terms of input IP3, which is simply the output IP3 minus the gain. So again, for amplifiers, industry-wide, most folks actually specify the output IP3, and that's a calculated value. So as far as the VectorStar is concerned, we have 3 options to carry out IMD measurements. The first option is you can do it using only the IMDView software, which requires external sources such as 2 signal generators and an external combiner also. That's option number 1. Second option is where you have both sources originating from the VectorStar VNA itself, but you have an external combiner. So the tones are actually combined externally. And for the purposes of this webinar, the setup that I'm using is where we have both sources originating from the VectorStar itself, and the combiner is also inside the VectorStar. So that's the advantage of that. It's a single connection measurement, reduces setup and measurement time. So you don't have to physically play around with any combiners or adjusting power levels of the tones externally. It's all done within the IMDView GUI itself. So that's the combination that we'll be using for this webinar. So here's the device under test, the DUT. I've chosen a very simple device. It's a mini circuits amplifier, the ZX60, which has a gain of around 10 or 11 dB. And as you can see, I've circled the IP3 specification. That spec is about plus 20 dBm. So the purpose of this exercise is to actually figure out whether the VectorStar actually measures that correctly, or how close we get to that number, the output IP3 of plus 20 dBm. So again, this is just given a bit of an overview. What does IMD involve? You have a VNA where you combine 2 tones. In this case, in our particular case, the combiner is inside, and those 2 tones are injected into the device under test, which is our amplifier. And then you have the output. You see a spectrum as if you see on a regular spectrum analyzer. You actually see the 2 fundamental tones, obviously with some gain as compared to the input. And then on the sides, you see the third order products, the 2F1 minus F2 and 2F2 minus F1. Those are the IM3 products that you see. And then we have the ability to do independent source and receiver control. What that means is the VectorStar not only has the ability to monitor the third order products, you can do 3rd, 5th, 7th, and up to 9th order products also. But most folks industry-wide actually just focus on the 3rd order products because they're the closest and sometimes fall in band, unfortunately. So then you have to do source and receiver power calibrations. This basically means that you inject accurate tones into your device under test. And then basically what's happened is the VNA has replaced things like the power meter spectrum analyzers for a full suite of amplifier measurements. It's a very useful tool when you can get a one-shot measurement. Now, this is the architecture. which we just spoke about earlier on. We have a second source, which is option 31. That's inside the VNA. And you have the combiner also, which is option 32. And the two sources are combined using the combiner, and they actually come out of port 1. And then you feed those, you inject those tones into the device under test. And then you monitor those at the output of the device under test using the IMDView, which is option 44. And then what the IMDView software does is it provides all of the configuration, computation, and the display of the intermodulation properties of the device. And you're going to see some plots on the following slide, as in what you see exactly on the VNA. So that's just a quick checklist of what parameters you set up in the IMDView software. You can set up things like the center frequency of the tones, the spacing. Then, as I mentioned earlier, you carry out power and receiver cals for each tone. Basically, power cal is carried out individually for each tone. That's the level of accuracy. And then the question arises, why do you have to do power and receiver cals at all? You do power cal because you want to know, you want to have accurate tone power at the source. And then the receiver cal is done because you take that known tone power and you transfer that knowledge at some source reference plane, and you transfer that knowledge to the receiver itself. And later on I have pictures which show you how these setups look like for both power and receiver cal. One thing to note here is you don't need a regular S parameter cal when you're doing IMD, and that's because you're not measuring any S parameters. You're only concerned about the power levels of the tones. Okay, moving on. To me, I'm a person, you know, a picture speaks 1,000 words. So here's the picture of the IMDView GUI itself. And as mentioned before, some of the parameters that you can set here is the mode itself. You have two modes. You have a spectrum view mode where you see the two tones as well as the third order products. And then you have a frequency, swept frequency mode also. You can set the, over here, you can set the center frequency, which I have set to 10 gigahertz right now. You have a tone delta. What's the spacing between those two fundamental tones? And then you can specify where each tone originates from. Now, and where it goes. In other words, for the second tone, it's coming from source 2 and it's coming out at port 1. This picture here, which shows the VNA, that shows exactly that. You have two, the yellow is the first source, the green is the second source, and they are being combined using an internal combiner, and both of them come out at port 1, and they are then injected into the device under test. And then you can set the power of each tone individually. Right now it's minus 10 dBm. And then you, again, as I said, you can set the tone delta, the source of the tone, as well as the tone power level. And the software, what does it look like once all this is configured? The following slides would show that. So before we see the spectrum, as I mentioned earlier, you have to do power cal for both tones. And this is how it's done. That's the actual GUI for doing the power cal. You calibrate each tone for power, and so the port 1, that's for the first tone. Port 1 is also for the second tone, but that's coming from second source, and that's, you can see here, you know, I've pointed the arrow here. So that's what you're doing for the power cal. It says your effective power is minus 10 dBm, so that's the power I will be getting at the end of my cable. And again, I have a picture later on which you can see. This is just a GUI for the power cal. I have a PowerMaster power meter, Enritsu's PowerMaster power meter, where I'm using it to do the power cal. It's a USB-based power meter, and I set the power level for each tone and carry out the cal for one tone at a time. And then, as you can see, the maximum error is like 0.03 dB, which is negligible, which is pretty close to minus 10 dBm. So that's the power cal. And as I mentioned earlier, these are the two setups that you use for both power and receiver cal. So on the left, you can see the power meter, which is connected to port 1 of the VNA. And you can calibrate one tone at a time using the power meter. The picture on the right is a receiver calibration. So once you do the power cal for each tone, you connect the two ports together using a female adapter in this case, which we call a bullet, and then you do the receiver cal. So now the receiver has full knowledge of the power levels of each tone that are present at the output of the test port 1 cable. So these are the physical setups that are actually used for this measurement. And here, after doing the power and receiver cal, you see the amplifier itself. This is the duty which you connect between the two ports. And you can see that little amplifier here on the picture on the right. So what does it look like once all this is done? This is what it looks like. So you can see a tone delta of 3 megahertz. That's what we had said before. Now this view, many of you are familiar with this view as seen on a spectrum analyzer. The two products on each side of the tones are the third order products, which we call the IM3. And you can see at markers 2 and 3, the output power is 0 dBm for each tone. And because as mentioned earlier, the gain of the amplifier was in the 10 dB ballpark, and we went in with minus 10 dBm. So this is what you see in this spectrum view mode on the VNA itself. So now the next thing is to calculate the output IP3 itself. How do you do that? So that's the formula, the difference in the two tones, the fundamental and the IM3. So in this case, I've chosen the upper, the second tone, upper tone. And you can see that the difference between the fundamental and the IM3 product is about the difference itself is 41.6 dB. So for ease, I just set the input power to minus 10 and the output power is 0 dBm. So using that formula, you can calculate the output IP3, and that's around plus 20.8 dBm. Now, if you remember, we spoke at the beginning, the spec for output IP3 for this amplifier was around plus 20 dBm. So the VNA itself measures very closely to that spec. So that's a good thing. We actually correlate very closely with the spec. And moving on, there are two modes to actually measure the output IP3. One is where you just have the spectrum view mode, where you have a fixed center frequency and a fixed tone offset. And it looks like a view on the spectrum analyzer. And the other method is where you use swept center frequency, where you use a range of frequencies that you want to measure the output IP3 over. And this will become apparent from the picture on the following slide. So as you see, the picture on the left here is just a spectrum view where you have to actually calculate the output IP3. The picture on the right is where I'm sweeping from 9 gigahertz to 12 gigahertz. The one on the left is just at 10 gigahertz, whereas the one picture on the left, the frequency sweep is between 9 and 12 gigahertz. And both of them correlate almost identical. And that's the beauty of this. You can see that the output IP3 on the picture on the right at 10 gigahertz, that's where I've put the marker, is around plus 20 dBm. And if you calculate the output IP3 for the plot on the left in the spectrum view, that's also in the 20 dBm ballpark. So both modes agree with each other. Moving on, this is very useful where you can actually measure things like S parameters, gain compression, spectrum view IMD, and swept frequency IMD, all in the same view. You have 4 different channels, which the VectorStar does allow you. VectorStar can go up to 16 different channels. But the beauty of this is that you get a one snapshot view of most of the measurements for an active device such as an amplifier. And I think that's a very powerful tool. In the past, we would have to do these measurements on different instruments, spectrum analyzers, VNA, and so forth. Here, the VNA can potentially be used to do all these measurements. So I think, again, that's very powerful. Here's an interesting fact between the IP3 and the P1 dB compression point. And some of you might already know this, but that relationship is that the output IP3 is roughly 10 dB above the output power at the 1 dB compression point. So for this particular amplifier, the mini circuits amplifier, the output power at P1 dB was around plus 12 dBm, and the output IP3 that we just measured was in the 21 dBm ballpark. So there's a difference of about 9 dB. So this relationship more of 10 dB more or less holds. So here is an interesting scenario. So what if the tones are unequal? What if most times P1 and P2, the fundamental tones are kept at the same power, but what happens to the relationship between these two tones and the third order products when the P1 and P2 tones are not equal in power? So there's the relationship. If you look at the picture on the right, if you have P2, for instance, which is 5 dB less in power as compared to P1, and that's what I've used for this example. The relationship between P2, which is the product on the right, the fundamental tone, and the relationship between that and the upper adjacent third order product is 1 to 2, meaning if P2 power varies by 1 dB, the power of the upper product, third order product, is going to vary by 3 dB. And then at the same time, the relationship of P2 to PL, which is the lower product, is 1 to 1. In other words, if I vary the power of P2 by 1 dB, the power of the lower order product is going to vary by dB for dB, which is 1 to 1 ratio. So on the next slide, I actually have an example of this, a numerical example. So what I have here is 3 cases. So let's talk about the first row. We already know that the output IP3 for this device is in the plus 20.8 or around 21 dBm ballpark. So in the first row, first example here, I have set the output powers of both fundamental tones to 0 dBm, and the output powers of the third order products is around minus 41.6 dBm. So then in the second case, I vary the power of the second tone, fundamental tone P2 by 5 dB. I drop it by 5 dB. So then what happens to both PL and PU? You can see that PL actually dropped by 1 to 1, which is it dropped by 5 dB also, but the PU, which is the adjacent product to the second fundamental tone, that actually dropped in a ratio of 1 to 2. So I changed the power of P2 by 5 dB and PU dropped by 10 dB. And again, I've cited the example numerically at the bottom of this slide. And then in the third example, I actually increased the power of P1 tone by 5 dB. And then you can see what happens to the tones, what happens to the third order products. So in that case, the PL actually goes down by 10 dB. Goes up rather, I'm sorry, I beg your pardon, goes up by 10 dB because I actually increased the power of P1 by 5 dB. So PL goes up by 10 dB, whereas PU goes up by 5 dB, which is dB for dB. So that's an interesting relationship. I just wanted to relay there. So what happens if the tone powers are not equal? So that brings us to a point. What happens? How do you set the tone delta? What is the correct value? What should be the difference between the two tones in terms of the frequency difference? So for most devices, the test protocols usually call out for the tone delta. So in this case, I've used 3 megahertz, but larger deltas will be generally easy to measure. And why is that? Because if you have the two tones which are too close together, you might get some noise contamination from the phase noise of the fundamental tones, and that might spill over into the third order products that you are trying to measure accurately. So generally, what is recommended for the VNA is as the delta decreases, so should the IF bandwidth. Now, in this particular case, I've used IF bandwidth of 1 kilohertz, which is more than sufficient for this measurement. It's like, so if the tone delta is 3 megahertz in this case, IF bandwidth of 1 kilohertz is, that means it's 3,000 times smaller than the tone delta. So we should be measuring the IP3 quite accurately. So that's just tells you that it's important to set the tone delta correctly. You shouldn't set the two tones close. They shouldn't be close together. Otherwise, you get noise contamination. And again, if you do, you knock down the IF bandwidth. Another important point I wanted to draw your attention to is the receiver power levels. So for the VectorStar, the 0.1 dB receiver compression point is around plus 10 dBm. So that's an industry best, as a matter of fact. The receiver IP3 itself is around plus 35 dBm. The whole objective here is that you should not hit the receiver so hard that it starts producing its own intermods. Because in any measurement like the IP3, you want to make sure that whatever IP3 that you're measuring is originating from your device under test and not something which is created by your own receiver. And you can easily test for that using attenuation. So let's say, for example, under normal circumstances, the delta, the IMD3 between your fundamental and the third order product is 40 dB. Now, even if you use attenuation, that delta should remain the same. If that delta increases, meaning if the IMD3 goes from 40 dB to, let's say, 45 dB, then you know that some of it was actually coming from your own receiver. So the whole idea here is care should be taken not to saturate the DUT itself or your receiver or your own receiver in the VNA. And the VectorStar actually does have internal attenuation built in also, so you can actually play around with that in order to set the correct level of attenuation if required. And that's just a quick summary of benefits for the IMDView software. The main one is this is very easy to use. All you have to do is go in there. You can put in the tone deltas. You can set the power levels, center frequency, and it's basically a platform for carrying out accurate IMD measurements. One thing I wanted to point out is you don't need to actually purchase a 4-port configuration when you actually add a combiner. And then finally, as mentioned before, right at the beginning, you have 3 choices of carrying out the IMD measurements. You can have the one which I'm using right now, where you have both sources as well as the combiner inside. You can just use the GUI if you wanted to and use both sources as well as the combiner externally, or you can just have the combiner externally and have both sources inside. So I think that's very powerful and gives you flexibility. And now I'm going to be doing a live measurement of the IP3 of an amplifier, which I've already connected. So what I'm going to be doing is I'm going to be presenting the screen of my VectorStar, and that should give you an idea. Again, as I said, picture speaks 1,000 words. So here it is. Here we can see the 2 fundamental tones. Both of them are at around 0 dBm, and you can measure the IP3 from this. 38 divided by 2 is around 19. So I mean, it varies. I know we had said 20 dBm before, but it varies. Depends on how long the device has been on and so forth. But it's in that ballpark. So this basically tells you. I just wanted to quickly show you the GUI itself, IMDView configuration. And again, right now I'm doing a spectrum view. You can do swept frequency or spectrum view. You can set the tone delta. which is 3 megahertz right now. You can set the certain frequencies. And as I mentioned earlier, right now the highest order I'm monitoring is the third order products, but you can actually go to 9 over here. And again, I'm just telling that the receiver is on port 2. IF bandwidth is 1 kilohertz. And then again, this is just a picture of which shows the particular combination I'm using right now, which is both sources are inside and the combiner is also inside. So this GUI is actually very simple and can be easily configured. And then that actually brings us to the end of the presentation. So if you have any questions, please feel free to ask them. Thank you.
Thank you very much. What is the maximum power level of the 2 internal tones?
So that really depends on how you want it to actually configure your device under test. Meaning, you want to make sure that your device under test does not run into compression. So I had chosen a point where I was actually backed off from the P1 dB of the amplifier by around 10 dB. So I had actually put in minus 10 dBm into the amplifier. How much higher can you go? The VectorStar can put out anywhere up to plus 5 dBm. But that's not something I wanted to put into the amplifier. And obviously, you don't want to put that much into the receiver either, because as I said, the receiver would also start going into compression and start producing its own intermods.
Okay. The next question, what is the IP3 of the internal combiner? Will it limit what you can measure for a DUT?
Yeah, and that's a good question. The combiners should usually have a very high IP3, meaning in the plus 50 dBm range. So, and that's mostly a passive device. So passive devices have very high IP3. I don't know the exact number. I can actually find out and take it offline, but normally combiners which are not active can have an extremely high IP3, which is also actually very difficult to measure also.
Okay.
So that's not something which would hamper the measurement.
Okay, questions are coming in now. Is IMDView available for the A model of the VectorStar?
I believe so. I don't know much about the A model, but again, let me take that offline. I don't know if that's actually available for the A model, but for the B, yes, definitely it is. Yeah.
Okay, when looking at optical links where gain can be minus 25 dBm, can it measure with loss?
Yes, it can. It absolutely can measure with loss. I mean, you just have to have enough dynamic range on your VNA, which we do. We have like in excess of 110 dB dynamic range. So as far as you can see the third order products, yes. I mean, as far as you're able to excite your device under test enough so that the third order products actually crop up from the noise, you should be able to measure them.
Okay, my last question here is the VectorStar the only product that can do these kinds of measurements?
No, there are many instruments out there which can measure IMD. There's these days a lot of network analyzers measure them. Spectrum analyzers were used to traditionally measure the IMD, but these days many modern VNAs can be used to measure the.
That is the last question I have.